Okay, so for your video review, the first question says, on the diagram above, label the vectors Vy, Vx, V, and A. So Vy is our velocity in the y direction, and you could have labeled any of these vectors as your y vectors, the ones that are pointing up or the ones that are pointing down. So as long as they're in the y direction, they would be the velocity in the y direction vector. So if you notice the vectors on the left side of this green, on the left side of the maximum height, all of those vectors show a trend. As they go up, they decrease. And then likewise on the right side, as they go down, they increase. So this is indicative of the fact that the magnitude of the velocity decreases as it goes up and increases as it goes down. The velocity in the x direction would be any of the red vectors, the short red vectors that are pointing in the horizontal direction. And one thing you notice is that they are all the same. That is because the velocity in the x direction is always constant. It is a non-zero constant. Okay? Alrighty, and then of course this is your velocity or your angular velocity. It's the actual velocity of the projectile in the trajectory. The other thing we have to label is acceleration. And you'll notice they only have one vector for acceleration. That's because for any general projectile, the acceleration is the acceleration due to gravity, which is constant, 9.8, and in the down direction. It is going to be up to you to write your paragraph. I will not answer that. So, to write the paragraph, you will take the concepts we just discussed, which go over these 6 sentence fragments. So you're going to use these sentence fragments to make a paragraph, string together sentences that make sense according to the content that we just talked about. And you can use one of these more than once, or any of these more than once. Next problem, let me get some room here, talks about 2 guys, James and John, diving from an overhang into some water. And the one, James, just drops straight down, while John does a running dive and dives off horizontally and then hits the water. The question is, assuming no air resistance, which will have the greater speed when they hit the water? So, the way you have to think about it, mathematically speaking, if you think about it, here is John diving in, and we know that we have discussed the fact that this would be the angular velocity, the vector from that would describe the velocity of him hitting the water. But in order to get that velocity, we have to take the velocity in the x direction and the velocity in the y direction and get the resultant vector, which will give us v. Well, it's very obvious here that this resultant vector v has to be greater than the y velocity. It's the hypotenuse or the diagonal there of that rectangle. So this velocity of him hitting the water at an angle is going to be much greater than him hitting the water going straight down. And that is what the other guy did. All he's got is his y velocity. So therefore, the one that dove, John, the one that dove off horizontally, when he hits the water, is going to be going much faster than the guy who just dove in straight down. Where am I here? Number 3. Same situation, James and John dive from an overhang into the lake below. One just drops, the other one dives off horizontally. They want you to compare the time it takes each to reach the lake below if there is no air resistance. So we know also then from videos and from what we discussed in class that because the only thing over time in the air is the gravity. Gravity is pulling you down, and gravity is pulling equally on each one of these. The rate of acceleration due to gravity is the same on both of these guys. That means then that they will both hit the water at the same time. Okay. There is another way of explaining this. At this time, I'm not going to go into it for the purposes of this test, but it involves the equal and opposite forces to explain why the time is the same. Number 4, the force on any rope or cable that suspends an object is known as the force of tension. No matter what class you're in, we have done this. My class did it in station lab, where you actually had to name the different forces that you saw around in different stations. Newton's third law and the terms of action and reaction explain what a force will exert on you if you push on the wall with a force of 50 newtons. So remember, Newton's third law is all about equal and opposite. For every action, there is an equal and opposite reaction. So if we're explaining leaning on a wall, the action is leaning on the wall. Whoops, it's writing funny. Hold on a minute. Is leaning on the wall. The reaction is the wall leaning on you. And according to Newton's third law, not only are they opposite, but they're equal. So the force of the wall leaning on you would be 50 newtons. Okay, define free fall and what property would give you the force of an object in free fall. Well, free fall is just falling under the force of gravity only. Or because of the force of gravity only. So that means no air resistance specifically. And the question is, what property of an object, such as properties of objects are like mass or color or position or weight, and what force of it or what property would actually give you the force of an object on the earth if it's in free fall. So the property has to be a force, and the property of weight would be the force that you have on the earth. So in other words, if my weight is 50 newtons, then when I'm in free fall, my force on the earth is 50 newtons, and the earth's force on me is 50 newtons. If an object is being lowered on a rope, but slowing down, how does the force of tension on the rope compare with the weight of the object? So this is almost kind of like an elevator problem. We have a force, your weight force, and we have your applied force going up. And actually, this is a slowing down problem, so this applied force is going to be a negative acceleration. and so therefore it, because it's slowing down, it cannot be equal to that weight force. There actually is an acceleration to it. It's a negative acceleration, but there is an acceleration, and it's preventing the elevator from falling as fast as it would if it was just under the force of gravity. So, and that force of gravity actually gives the elevator its weight, or weight force. So therefore, that tension on the rope has to be greater than the weight of the object in order to slow it down, in order to keep it from accelerating at the rate that it would have if it was just under gravity. So there the answer is greater. However, if it's being lowered at constant velocity, well, then that means that your applied force has to equal your weight force, because if it's at constant velocity, there's no net acceleration. If there's no net acceleration, then these two vectors must equal each other. So if it's being lowered on a rope at constant velocity, then it equals the weight of the object. Okay, so you're having a tug-of-war game with your friends after school, and you have reached a stalemate. Your team is pulling on the rope with 1,000 newtons of force, and so is the other team. What is the force of tension on the rope? Most people will answer one of two things, either 1,000 either 0 or 2,000. And 0, if you think about it, has to be the wrong answer, because if I have 0 tension on a rope, it's going to slack. It's not going to be taut. And we're in a tug-of-war, and that rope is going to be taut. It's understandable for people to say 2,000, because they say, well, then we're just going to add together the force. What you have to realize is that in a tug-of-war, you actually have to think of the rope as an object. And so here's team A, and here's team B. And what you have to think of is two separate third law systems. So we have the force of team up, excuse me, let me get that back up. We have the force of team A, which is 1,000 newtons. We have the force of team A on the rope, which means the rope applies a force to team A, which is 1,000 newtons. As likewise, on the other side, we have team B that applies a force of 1,000 newtons on the rope, and the rope applies a force of 1,000 newtons on team B. So therefore, the overall tension in the rope has to be 1,000 newtons. Okay, considering this pulley system below, Part A says if mass 2 were just hanging motionless by a string by itself, in other words, it wasn't on a pulley system, it's just sitting there hanging from the ceiling like so. All right? How could you find the force of tension on that string? So we would have a tension force up here, which would be actually our applied force going up. And of course we have the weight force. Well, if it's just sitting there motionless, then that means the weight force has to equal the tension force. And so the weight force would just be the mass times acceleration due to gravity, and we would get the tension on the string. But now let's tie that string to another mass. I'm going to take our mass 2 and we're going to tie it to another larger mass here, mass 1, and we're going to allow that, that mass to slide on a frictionless surface. Now what is going to be the tension on our string? In this case, the tension is actually going to be less than, I'm going to call this force of tension FT2 and this FT1. FT1 will be less than FT2. That's what B asks us. Okay? B asks us what would be the tension on this string now. So understand that no longer is this mass just hanging here and the only force on it is the weight force. There's now another force acting this way, acting up. Let me erase that. Up. There's another weight force, there's another force acting upwards due to that sliding mass. And because of that, and being directed away, the tension on there is actually going to be less than if the mass was just hanging. Okay, so good luck on your test tomorrow. If you got any questions immediately before the test, I should be at school by 6:30. It's going to be cold tomorrow, guys. Put on your coats, your mittens. Going to have freezing temperatures. Wrap your pipes, all that good stuff. Okay, so bye for now. Bye-bye.